Hello. I wanted to do a brief sort of introduction into the field of data science. Sometimes we are using words that we think we know what they mean and we may not. So this may be old news for some, but it always is helpful to be very crisp in what we talk about things. So jumping straight into it, what is it? And this is the heart of it. It's the science of data, not terribly helpful as far as definitions go. It's a discipline focused on deriving value from and understanding data a little better, and it's the applications of statistical and other methods of data. You basically are combining together the statistical techniques that we've used for years in the field of data analytics with artificial intelligence and a few other disciplines to solve problems and derive value from data. That's the whole point. And we do this in a new number of ways. And the primary motivation here is to be able to do it in an automated way, ideally. Now, you may not be able to because it may be that you're doing analytics for a particular problem and can't necessarily generalize that to a production type solution. But if you can, that's what you want to do. In general, the areas and techniques and theories that are related to or part of data science are things like clustering, association, regression, the classification, time series analysis, text analysis, and then some things that you lump into maybe a bucket of things like advanced topics, right? And in that bucket, you'd throw in things like artificial neural networks, support vector machines, genetic algorithms, and reinforcement learning. This isn't an exhaustive list, but it's not a bad one to go from. So clustering, what is it? And it's basically an unsupervised method, meaning we don't know what the answers are. Instead, we have some data. We want to try to understand that data in some way. And we do that by applying algorithms to it to try to see if there is some sort of groupings inside of that data. And it's often kind of visual in nature in that you may want to be able to visualize it to really kind of understand it. How do you do it? Generally, you'll probably be using some sort of k-means variant. It's a centroid based approach. There are other approaches, hierarchical clustering, mean shift, and so on. But oftentimes k-means is what you're using. K in this context is just a number, and in general, it is the number of clusters you're looking for. So why do you do it? You may want to do it to try to determine if something is fraudulent or not. You may want to be able to figure out if a person has a certain disease or likelihood of having it, identify things that are similar, such as marketing personas, doing market segmentation, and maybe even imaging. And then generally speaking, you do it whenever you want to try to either binary or categorically determine what cluster or what set a piece of data belongs to. It generally looks something like this. This is an example of an interactive k-means algorithm being ran. You tell it the number of centroids, that's k. You have it give it the data that it's looking at, and then you basically tell it the number of steps to run. So it's just running through in an automated way for you to visually see what it's doing. You can see that it's shifting the centroid around, trying different values in different groups and determining which ones that particular value is closest to the centroid of. So it's an interesting thing to watch, but it also does rely on things like randomized starting position. And by starting in a certain random location, your outcomes might differ. So it is something that is useful whenever you're dealing with data that isn't labeled, meaning you don't know the answers, but it doesn't solve all your problems. Another very popular approach is association rules. And you may also hear this referred to as shopping basket analysis because that's one area where it is frequently used. It's basically a way of giving some historical information, make some predictions about grouping. And it's a form of unsupervised learning, meaning you don't really have a labeled data set to work from. You have some historical data of some sort, maybe transactional data, and that's where the name kind of comes from. This is something that was widely exploited and continues to be widely exploited in the realm of e-commerce. How do you do it? Oftentimes you're using the a priori algorithm, and there are other approaches. You may iteratively prune items from the data set. you're essentially looking for if then else sort of relationships. And why do you do it? To sometimes make predictions or recommendations, if you will. So it might be if people have bought these 5 things in the past, maybe they also typically include this 6th. And the sort of seminal explanation of this is the what is it, diapers, beer, and bread or something that is often purchased together. There's a typical pattern there that emerges over time. And the way you do this is oftentimes by trying to improve the customer's experience, as well as they would say in retail, completing the sale. And examples of this are in other spaces outside of retail is the suggested videos in your favorite streaming service. They'll often say, since you watch this, you may also want to watch these other videos. Regression is a way of trying to essentially fit a line to a collection of values, right? And you're trying to figure out the interaction between these variables or features. And you focus on determining how one variable or feature impacts the outcome of another. And generally, you're trying to fit something to a collection of points. It might be a line, a plane, or a hyperplane, depending upon the dimensionality of your data. And why do you do it is to try to figure out what things might be changing the impact of outcomes. You may also try to do it to make some sense of prediction into the future. Classification is similar to clustering, but it's more general in the sense that you're trying to figure out what class a particular item belongs to. You may do it in a k nearest neighbor sort of approach, similar to what clustering is doing, but you may also do it through other mechanisms such as decision trees, naive Bayes, and neural networks. And the reason that you might want to do it is maybe it's simple classification of, is this a Boolean value of spam or not? Given some data points about it, perhaps the length of the text, the number of misspellings, the number of email addresses that are receiving it, and so on, you may be able to determine if it is, and if this is something that is being done consistently. Transaction classification being another example, not only looking for things like fraudulent behavior, but also looking for things like, is this a household expense, a shopping expense, entertainment, and so on, to perhaps help you in your financial planning. The typical pattern that you follow with a lot of other sort of things potentially as well is you'll load the data, you do some exploration of it. You'll want to be able to separate out the attributes and the labels, that is the values that are going to be used to predict versus the thing that you're trying to predict. And then you'll typically split into test, train data sets. You may also include a validation set as well that may be used during the training process in combination with the train data set, or it may be a subset of the train set, to essentially determine how well you're doing as you're doing the training. You'll then oftentimes standardize through a transformation the values, and you do that in order to bring them into the same essentially scale. It might be from -1 to +1, or it might be that it's applying some transformational formula to it to make sure that things are essentially kind of contributing the same amount to the outcome. And then you'll create a classifier, oftentimes by calling fit on the model. Once you've got that model, the whole point of any kind of model, generally speaking, especially in data science, artificial intelligence, is to use it. And that's sometimes called inference, sometimes it's called prediction. So you're using that classification model, in this case, that you've trained to make predictions of the future. Then you're going to check the accuracy using that test set that you've held out and that hasn't been used in the training process. The last step of that is typically to, once you've done all this, you're not done until you actually are able to run it in a production environment, generally speaking, because that's the whole point, is to train upon known things with the intent of making predictions against unknown. Another sort of thing that we often do is time series analysis, and it's a segment of data analysis that has a temporal element to the data. So that's data points that are essentially collected over time, and there may be multiple points over time. And the types of patterns that you may be looking for, or general trends, are the things that go up and down, is what is the things that are changing the direction, and so on. Seasonality, potentially things that have a cycle that they follow. Potentially sales are higher at Christmas. And you may have something that's a similar seasonality, which is cyclical movements, but it's observed after a few time units. It's not nearly as frequent as things like seasonality. So think sunspots that occur every 10 or 11 years, whatever their cycle or their frequency is. And then you may often have these things that are unexpected variations. This is something that occurs that no one saw coming, such as COVID, that will really make it such that it's almost impossible to do prediction, at least based upon historical values, because you're in a new reality. Additionally, war is something that might do that. Some sort of impactful event that occurs, change in government, whatever it might be. How do you do it? There's lots of different various ways of doing it. Autoregression is one that is very common. Why do it? So you want to look for patterns in your data over time. The text analysis is extracting information from unstructured text. So think of a tweet on X, whatever, assuming they're still calling them tweets, or I guess there's maybe X's, I don't know. Anyway, you get a chunk of text that by typical analytic analysis or usages of analytic patterns is not terribly useful. So you'll do something like text analysis to attempt to learn something from this unstructured data. You typically will be doing things like topic determination, looking for sentiment. Is it a positive or negative kind of statement? Looking for answering questions, locations, and so on. This is an area that generative or large language models have become very useful and helpful, because the natures of large language models lend themselves to this nicely. In particular, a segment of that field called basically augmented retrieval is done to essentially do a generative approach to retrieve data and so on. It's often called RAG. Anyway, advanced topics, these are things that don't fit nicely into the other buckets. Neural networks, very impactful, and I just talked a bit about one of those, which is large language models. That's a subset of traditional deep learning approaches, right? And the thing that makes it much different, several things, but a lot of it is the size of the data involved, as well as the type of approach that's being utilized. You generally want to use neural networks to do things like transform data. You essentially run it through something that has a number of inputs. There's some weights that correspond to those inputs. There's usually some form of kind of calculating across it and potentially introducing a bias to move things around as needed. But it's all about adjusting those weights over time, and it's essentially propagating the data error back through the neural network so that it's impacting the weights to improve the quality of future predictions. You'll do this for lots of reasons. Regression and classification are two good, very common approaches. Support vector machines are an interesting field. It is a supervised learning approach, meaning you do know the answers. There is a labeled data set. And it's basically done by increasing the dimensionality by applying a transformation to all of the data points. And by doing so, you can using this kernel function, essentially make it so that you can separate things that previously couldn't be separated. As you see on the top right, the stars in the middle can't easily be separated by a line. A circle could do it, but it's really hard to do a circle in this field for this kind of stuff. However, if you apply transformation, you can then do a line to separate them. So it does, it's an interesting sort of approach. There are different types of kernels that do this: linear, polynomial, exponential kernels. And again, it's about being able to separate things that otherwise are really challenging to do. Genetic algorithms are a little bit of an older technology, but it is pretty cool. It's based upon the concept of Charles Darwin's theory of evolution. It's a heuristic search, and you're basically creating a population. You're defining a fitness function, so a way of determining to an extent what good is. You then select some parents, make some crossover, essentially the combining elements from both parents, and then do some mutation with some random sort of changes. And you can see the kind of the high level algorithm on the right side. Really cool stuff, a good way of solving complex problems. And it isn't as popular as it once was, but it is still quite important and useful. And then another kind of the last one of our advanced topics is reinforcement learning. This was an approach used by the team that beat a Go master by not trying to exhaustively calculate the search space, meaning figure out all the answers ahead of time, but instead you basically have a way of determining what is good and what's not good. It is essentially a connectionist approach to unsupervised learning, meaning it doesn't necessarily have to have a labeled data set, but it does need a way of knowing what is good. So you have to have a scoring function of some sort, similar to the fitness function of the genetic algorithms. So you typically are programmatically balancing exploration with exploitation. So you use what you know and then look for better ways is the basic idea. And there are various ways it can be done. There's passive, where it watches without being able to change. And then there's actually active learning, where the algorithm will make changes to the thing that is being observed and then be able to react accordingly. And it is done when the search space is impractical to traverse using traditional approaches. And that's an example of Go. There's just simply too many move variations. And it does not require, because it's a unsupervised method, a labeled data set. And with that, we've reached the end. As always, if you have any questions, pop them into the comments. Like and subscribe, as always. And hopefully you enjoyed this. I'll talk with you later.